Hi everyone, today we are going to continue reviewing linear equations, except that this time we are going to compare linear equations to exponential equations. So our objective for today is to identify real-world scenarios that are most appropriately modeled using linear or exponential relations. Remember, the reason we are doing this is because we are analyzing data for our integrated assignments. And when we analyze data, we look for patterns. And one of the patterns we look for is identifying whether there is a linear relationship or an exponential relationship. So since we're going to talk about exponential equations, let's first review foundational information about exponential equations. One way to define an exponential equation is listed here. In an exponential equation, there's a pattern where the same number is consistently multiplied. This is different from a linear equation because you might remember that in a linear equation, there is a pattern where the same number is consistently added or subtracted. So here we have a pattern of multiplication rather than a pattern of addition or subtraction. Exponential equations follow this format. Y equals a times b to the power of x. A represents the starting value, also known as the y-intercept. This is known as the y value when x is 0. B is the growth or decay factor, depending on whether the numbers are going up or down. If the numbers are going up, we call it the growth factor. If the numbers are going down, we call it the decay factor. This also represents the repeating pattern. And as usual, x is the input, y is the output. This is an example of an exponential equation. Y equals 80 times 1 over 4 to the power of x. So here our starting value, our y value when x is 0 is 80. And we see that reflected in the table. Our factor is 1 over 4. In this case, it is a decay factor because it will cause the numbers to go down. So as we can see here, we're repeatedly multiplying by this number. We're repeatedly multiplying by 1 over 4. And it's causing the y values to decrease. Here's another example of an exponential equation. Y equals 1 times 2 to the power of x. Here our starting value is 1. So that's the y value when x is 0. And we see that reflected in the table. Our factor is 2. And in this case, the factor is considered a growth factor because if we repeatedly multiply by 2, it will cause the numbers to go up. So as we can see in the table, we're repeatedly multiplying by 2, so the y values are increasing. Quick review on exponential graphs. So another difference between exponential and linear equations is that exponential equations do not form a straight line. Exponential equations form a curve when graphed. The reason is because the numbers increase or decrease very quickly. So since the numbers are changing very quickly, this causes the graph to form a curve instead of a straight line. When the y values are increasing, the b value, also known as a growth factor, is greater than 1. Remember, this was the b value. If the y values are increasing, we're going to call this the growth factor. And we can tell that the y values will be increasing when the growth factor is greater than 1, such as we saw in this situation. The growth factor was 2. That's a number greater than 1. So it caused the y values to increase. And in that case, the curve is going to go up, as we see here, when graphing that equation. When the y values are decreasing, the b value, also known as a decay factor, is between 0 and 1, and the curve will be going down. So as we mentioned before, if our b value causes the y values to decrease, we'll call it the decay factor. And we know that the y values are going to be decreasing if that number is a number between 0 and 1, as we're seeing here. 1 over 4 is between 0 and 1. So when we multiply it by 1 over 4, that caused the numbers to go down, which means that the curve is going to go downwards when graphed, as we're seeing here when we graphed the equation. Now, another important thing to remember is that exponential equations are not always expressed in this format. This is the most basic format that we describe exponential equations, but we also think of them in these formats. Y equals a times 1 plus r to the power of x, or y equals a times 1 minus r to the power of x. The reason we use these notations is because these notations help us to identify this information here, the r value. It helps us to identify the growth or decay rates. For example, let's say I wanted to express my first equation in this notation using one of these formulas. So remember, the first equation we looked at was 80 times 1 over 4 to the power of x. Really, the only part I have to focus on is what's inside the parentheses, because notice that's what changed. Y is still the same, a is still the same, x is still the same. The only difference that inside the parentheses, I'm not using b anymore to explain what's happening with the growth or decay. This time I'm using 1 plus r or 1 minus r. So I'll know which formula to use depending on whether my exponential equation represents growth or decay. And remember, in order to determine whether my equation represents growth or decay, I have to look at the factor. Remember, we said that this factor will cause decay to happen. So since I know that this equation represents decay, I'll have to use this formula to determine the r value. Notice this formula has subtraction in it, representing decay. So first thing I can do is I can express 1 over 4 as a decimal. If you divide 1 by 4, that's 0.25, right? So I expressed 1 over 4 as 0.25. And then what I basically do next is I determine how was that 0.25 calculated using this notation. In other words, what was substituted in place of r for me to end up with 0.25 inside the parentheses? What was subtracted from the number 1 in order to get 0.25? And the value that's subtracted from 1 to get 0.25 is 0.75. So you can also think of this formula in this way, is 1 minus 0.75 inside the parentheses. And once I've written it in that format, that helps me to determine the r value. Now I know the r value is 0.75, so now I know the decay rate. Using this notation, we determine the decay rate is 0.75 or 75% decay. Basically meaning that every single time we're decreasing the numbers by 75%. And that makes sense if you think about it, because if we're multiplying by 0.25 consistently, that means the numbers are only keeping 25%. They're keeping 25% of the original value, meaning they're losing 75%. So that's what this basically means. 75% decay, meaning that the numbers are consistently losing 75% of the original amount. Let's say we wanted to use this notation for the second example, for y equals 1 times 2 to the power of x. I would have to first determine which formula to use. And I would determine that by looking at my factor. My factor is a growth factor. It's a number above 1. I know it's a growth factor because it's going to cause all of the values to increase. So I'm going to use this notation, and I'm going to look at what's inside the parentheses and ask myself, how was that number inside the parentheses calculated? So in other words, what did I substitute in place of R to get a 2 inside the parentheses? What I substituted in place of R was 1. So 1 represents my R value. Using this notation, we determine the growth rate is 1, or 100% growth. Remember, 1 in decimal format, if we think about decimal values, 1 represents 100%, meaning that these numbers were growing by 100% every single time. Which makes sense because when you're growing by 100%, that means that you're basically doubling. That means that you're keeping 100% of the original and adding that on, which is what we're doing here. We're doubling the number every single time, meaning we're adding on 100%. Here we were deducting 75%. So that's why these numbers are decreasing so quickly. We're only keeping 25% of the original amount. We only kept 25% of 80. We only kept 25% of 20, meaning we lost 75% every single time. So that was a quick review. You should have learned all of this before in algebra, but this is just here for you to look back at in case you forgot about the essentials of exponential equations. Now let's try some examples.